Okay, thank you, and welcome all for the presentation. So we will have. Hope you had a good lunch, and then as usual, you had a good energy. And let's go into the source separation model that we have applied for Indian classical music and semi-classical cinema compositions. Here I will be showing only some I'll be showing only some open source classical compositions that has been published in Saraga dataset. That is a very famous dataset from the MTG group of Spain. We have taken some pieces, and then you'll be seeing some segments out of that, and then that will be taken for the source separation models, and we'll be showing it to you instead of only the cinema songs because of the copy. As usual, the copyright issues, we cannot show those things here. So, hope everyone know here what is the importance of source separation, and it has a very long history, at least minimum 30 to 40 years in DSP. It started all with the DSP and then advanced signal processing techniques, and then now it has been entered into music signal processing. Of course, it is there. Then our AI came into part for playing inside, and we have started applying for the past 4 or 5 years after the invention of the neural networks, so the attention models and transformer models. We have started applying those things inside the source separation models, and like that we have taken some architectures and we have tested on different types of music genres like western music and then Indian classical music, and of course our cine music, which is semi classical in nature. It is we have a total western background, but it has an Indian flavor applied over there to that. So like this we have several combinations, and then we have taken some tracks, and then we have applied those things to the different models, and the majorly we have taken two models. So here you see here that the Indian classic music system mainly works with, it's not just the an octave of C, D, E, B, A, B, C, the 12 notes. It is totally based on the swara system, which is working on microtones. It is not working just on the notes or just the frequencies, because the ragas are totally dependent on the microtones, and that microtones have glides and slides and the gamakas, what they call, which creates the microtones or anuswaras they call in ragas, and then you get these kind of complex rich structures for expressing our emotions there. So these kind of things are present inside our system, and we need to separate this music from the as these models, the AI models which are all designed, are not designed for this kind of an architecture. They are designed for totally for the Western system, and so we need to apply such kind of a Western architecture to our system. What is the result? We will see that. And if it is not going to work good, hypothetically we think that it is going to separate the rhythm separately, and then the beat separately, and then vocal separately, like that we are going to think, but we hypothesize that, but it may not be the case. It may not happen for our system. We will see what happens. We have taken two, if what are the problems or challenges that we face, and what can be changed over there so that it can be applied to our system or the Indian system. So it can be applied by the composers, because the composers are the main people who are going to reach the public, and then we need to create plugins. We have a lot of developers here who can create plugins out of the source separation models, and we can give it to the composers, which they can reach the public. So this is what is very well given here, because here the string instruments, already in Western string instruments have the bleeding problem over there, and here also the bleeding problem is very high. Bleeding is, what is bleeding in source separation? When you separate a vocal from the others or all other beats and others, this vocal will be infested with all other the string instrument sounds. That is a timbra overlap they call, and then this will be entering inside the vocal thing, frequencies.
आराधयामि सततं मदनारीश्वरम् आराधयामि सततं मदनारीश्वरम् आराधयामि सततं मदनारीश्वरम्.
Okay, so we heard a classical music piece which consisted of a violin, a mridangam, and then a vocalist playing over there with a drone or a shruti being played at the background. So when you like to separate, what are the three things? It's so simple. It is so we need the vocal separately, a violin separately, and the beat or the tala, which is given by the mridangam separately. We have to have these three structures separately coming out of the model. But is this going to happen or not? We will see using the two different types of architectures. So what is this kind of a general classification challenges? As I already very well explained, the timbral problems. What we have, the string instruments colliding with the vocals, and that too, this microtonal variations that what we see in the raga also plays a very complex part in vocal separation there. That is one main overlapping problem of the timbral problem. Then the annotated data sets, we have only one data set, that is what is available now, and we have used it over here because for the Carnatic and in cinema data sets we don't, that also we don't have. Only in the Saraga data set we have for the Carnatic, and we have used it here because for an annotation purpose it is very tough to annotate and take it, as usual for all IA models. Again, I want to again and again say about this microtonal variations are the very important things in our system that will create the model more and more complex, and because it is not totally separated out, the frequencies are not totally separate, we cannot simply apply an MFCC coefficient or else a chroma feature over there and then extract out all the information. We need very specific deep understanding of the MIR, music information retrieval features, that is which feature is going to act on which area, and then can we get that information out of that. For that we need a very deep understanding of the music information retrieval features or the attributes that which is going to contribute into the AI model, and these kind of things are much important. And for that we have to in depth we have to understand the model, and then only we can apply that model for our mm, mm, test patterns for the use case. And also they have the dynamic rhythm patterns, the tala can change and then the beats change, the tempos, there are the gadi systems are there inside our music. Those are not that much the complicated maybe in western, but I'm sorry, I'm not very good in western beats. Okay, here these gadi patterns are there, and then separating out those gadi patterns and all those things are also a very big tough job over there. As actually I told, the timbral overlaps. You have a vocal, you have a string instrument veena over there, and then if you have a nadaswaram over that, it is very tough to remove the bleeding out of that, because nadaswaram and veena will entirely have a timbral overlap over the vocal things, our vocal frequencies, which it will merge there. We have tested it very well. We have tested this nadas when you have a vocal someone singing there, and then when you some the other track is totally overlapping over there, the nadaswaram track is overlapping over the vocals track, then we will not be able to get properly the vocal track. It will be totally bleeding will be occurring there in the vocal track. And also if you have a veena track over the vocal track also, the same problem will occur. So only in Carnatic music concerts, or you won't find so easily a vocal being heard along with a veena, or else over an adaswaram. It will be played separately. The vocal will be first they will be singing, then the veena will be, all other instrument also will be going on around. You can take many concerts, you can see these things also there. So next things about the annotation of the data sets, and then what are the two types of data sets the models we have used. One is a Demucs model and the Spleeter model, both having a very different kind of architectures, but both works on the neural network architecture, but the arrangement of the architecture is different. Those things will be explained by the by Dhayanithi and Pawan. You can just go on.
So, like Sir said, we have very limited data sets for training the models on the specific genres. Like we have very limited data set. We have the well-known Saraga data set, uh, which is recorded from live concerts, which may contain bleeds and bleeds of other instruments also. So we 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 shall go through the existing source separation, well-known source separation models, which is first Spleeter, which is a unit-based model. Unit architecture is basically a image classification architecture, which is then transferred to audio field also. So this works on unit-based architecture. Like audio is converted to spectrograms and then it is processed to in unit architecture, and three kinds of models are there available, like they separate 2 stems, 4 stems and 5 stems, like. And then it comes to Demucs, which is time domain, and also it also takes unit, it also incorporates unit architecture also. It works on raw audio waveform and also with spectrogram also. So it's a hybrid model, and it takes much computational resource and time also to separate the sources. And then there are OpenUMX, which is also a spectrogram model, and XUMX, enhanced version of UMX, and MIDX model. So we can compare the top two models, which is Spleeter and Demucs, which gives better results when it is tested with these kind of genres like classical music and semi-classical music. So as we saw, architecture are both similar, but Demucs has one which it works on raw audio form also. Speed comparatively, Demucs is time consuming because it works on raw audio. So when it is passed through neural LSTM, it takes time to analyze the patterns and then outputs the various stems. So the speed is comparatively Spleeter has the fast speed. Like separation quality, as we saw, Demucs is though time consuming, but it separates stems clearly by as compared to separation Spleeter. So this is the separation quality. So use we can use both these models for our use case, and it's easy to use. So uh, they they come up with different models. Like Spleeter has 3 models, and Demucs also has various stem models, like 4 stems, 3 stems, and up to 7 stems, I think so. So these are the just we analyzed these models with our audio track. So this is the original spectrogram. First is we took a original vocal track and compared it with both the sources of Spleeter separated vocal and also Demuc separated. So as we can see that how what is the audio.
आराधयामि सततं मदनारीश्वरम्.
So as I said, there is uh, very few dataset which is very which has the quality like original quality. So as compared to Western, it is low quality is low for the existing classical datasets. So this is the vocal, and this separated from
Varadayami Sadadam Danarishwaram.
So we could hear that with vocal Mridangam also is bleeded in this vocal part. So Spleeter struggles to Western trained. It is trained with Western dataset, so it struggles to uh, remove that Mridangam because of that peaks, strikes in that which comes across the vocal. So it struggles to separate the sources clearly. And as we compare with
Varadayami Sadadam Danarishwaram. Varadayami.
so we could hear that this is a little bit clear compared to Spleeter because it is a hybrid model, and it takes time to separate the source clearly. So this we can see the scores, it is in the negative, so because of the quality of audio we have, so comparatively Spleeter gives the score better for the classical musics. So as we come here, we take Spleeter for the Carnatic classification because it is based on unit architecture, and it requires less data set comparatively to the Demucs architecture. Demucs is a hybrid model which requires a high quality dataset and high resolution dataset. So we try to improve this Spleeter model for this particular genre, which has unit architecture and gets the spectrogram inputs, which contains encoder for the encoding signals, like splits the features separately as it moves through the model. So it has also skip connection, which is used to transfer the low level features directly to the decoder. So we will not lose our fundamental frequencies of the audios. So this skip connection is used for that, and it provides various models for Splitter has some models to separate various stems. So working architecture and improvement of this model will be delivered by Dhayanithi.
Okay, hello. Okay, so for the source separation models existing in a Western music system, explained by Pawan, we have seen so much of source separation models. Within that, we have selected two models, which is both are also open source models. One is Spleeter and another is Demucs. So why we chosen those models is that both models are deeply working in using unit architectures of neural networks model. So now we get into the working model of Spleeter. So basically, Spleeter is an open source tool. It is developed by Deeger, which uses deep learning to separate tracks into audio tracks into pieces, which such as vocal, drums, bass, and other instruments. So basically, Spleeter model works on spectrogram based input. It converts the audio file, in which we can see here. The audio file is taken as input and is converted into spectrograms for short-term Fourier transform, which produce a time frequency representation. Then the spectrograms are further processed into a unit architecture, which is contain encoder port and the decoder port and a bottleneck. As it is a unit architecture. In the encoder path, it captures the high-level features and it undergoes dimensional reductions. So in the bottleneck path, we can behind the scene and layers, the abstract features are marked from one layer to another, from first layer to the final layer. Not every features are contributed to for the source separation project. Ultimate goal is to split the audio file into audio pieces. So for that, which features are mainly used to for that separation, that can be extended from the abstract features. Then in the decoder part, it concatenates features from the corresponding layers, and then the abstract features which contains the data of the unique pieces are then gone to a masking layer, which predicts soft marks for each sources. So from that we get the output of different stems. For example, if we had the audio file containing two string instruments and one percussion instrument and the vocal, and it will be, we can by this process the model will give output as vocal and guitar, strings, sorry, and a percussion instrument. So this is the working model of the Spleeter. So basically, what is our idea? We have the Western source separation model, which is trained fully on with Western data, Western music instrument data sets. So our goal is to build a model or fine-tune a existing model for perform well for Indian classical music instruments. So so we choose a splitter model. So we have in previously I have said the abstract features. So we can see the what are the features that are selected in the abstract layer. So these are the 9 features just responsible for splitting from audio file to stem pieces. I just playing 2 audio file. What inside the audio file is first audio file is contain Indian classical audio, which contains 2 instruments. One is Veena and Mridangam played audio, and another audio is having a Western audio piece having guitar and drums. I just play the audio for a demonstration. So we have seen that in classical music piece, we just hear the Western music piece. So basically, these two pieces are fed into the model and analysis based on the extract features. So these graphs are contains all this first graph says a chroma feature plot of both audio phase. That red color line shows the Carnatic audio piece, the graph of chroma feature of Carnatic piece, and the blue color line shows the chroma features of Western piece. So it is well known that Spleeter model works well on Western data. So the Western piece of chroma feature is very precise. So while we using on to Carnatic Indian classical piece, we can see how the relation between the 2 pieces it can be seen in this graphs. how the model perform well for it's not performing well, but it's okay, somewhat working for Indian classical instruments also. These are the features we can see. Okay. So based on the features for abstract features, what is the observation we have find? We have to improve the existing architecture of Spleeter with these techniques, and it can be performed so well for the Indian classical music system. So these are the techniques like melodic structure, improvising the melodic structures and overlapping timbre techniques. Using these techniques, we have suggested some filters also. By using these techniques, this same Spleeter models can also perform so well for Indian classical instruments. Okay. So we have this same related works are we have a reference taken from music technology group music technology group of Spain, Barcelona. Okay, thank you for asking.
So it is, as you have seen, it is not a complete entire project being finished, or we can't. It's only in an observatory case we have taken, and they have applied several changes to the MIR features, or the features, or the attributes that can be given to the model, and they have tested over there, and they are able to get some very different results for different types of musical pieces, and we are working on that.